Good. Okay. So today we talk about performance-based designs for complex structures and how software enables new innovative workflows. I tried to keep it super simple. We can always dive deeper. I made sure we have enough space at the end for questions. So if you think we need to dive deeper, you have any questions, try to keep it to the end and we can discuss it all. And after the presentation, I try to stick around. So if anybody has more questions, you can find me probably on the main stage. So today, for everybody who doesn't know Autodesk and the company, I give a really brief introduction into the company. I give a brief introduction into who I am, because I guess some of you or most of you don't know me. We talk about performance-based designs. What does it mean? I will explain a little bit what is Autodesk approach, what are we doing, and then we talk a little bit about the software ecosystem and what else is important for it. And in the end, as I said, we have lots of time for Q&A. So myself, Dominique, I started working for Autodesk almost 7 years ago now. As you see, I have always had a passion for additive manufacturing, so I have always been part of the additive team, and especially the software development team, so the team that works on NetFab, the team that works on Fusion, the team that works on Palmel additive solutions. And last year, I started a bit of a shift in my career, so I'm now the product manager for research and innovation. So I'm helping the team to plan ahead on what's coming in 5 and 10 years, what kind of trends we need to prepare for, which kind of technology we need to prepare for, and how the software needs to develop to be able to also keep up with future things that are coming up from customer partners, ecosystems, competitors. So that's my new role. It's not completely focused on additive anymore. It's focused on whole manufacturing now. From my education, I have a master's degree in material science and engineering, and I have a bachelor in microsystems technology. And I switched over to software pretty quickly after my education. I'm from Germany originally, so I'm born in Germany, but I live in Denmark. And I live in Denmark because there's lots of water, and I love water sports. And yeah, my husband, he's Danish, so that's why we're living in Denmark. Autodesk is a software company. We have 3 main areas. Manufacturing is one of them, and that's the one we're looking into today. But we are also pretty big in the construction industry, as well as in the media and entertainment industry. One thing a lot of people don't know about Autodesk is we started to have technology centers. So we opened up several facilities to have our own equipment, to test things, to develop our software further, to test our software, to work on customer problems, and just to gain the knowledge about machines or the technology we need to work with. There are 6 technology centers at the moment. We have one in Canada. That's our machine learning and AI laboratory. So we're doing a lot of experimentation around machine learning and improving the software in Canada. Our Boston facility is very much focused on construction. So we have a lot of robotics there. We have fabrication there. We have a lot of startups joining us there, so they can get their own space. And we have a program there where we onboard them. They can use our machines and they get the training for the machines, for the software, for everything they need. Similar in San Francisco. We also have a lot of startups there, but this one is very focused on robotics and digital fabrication. And we have 2 in Europe. We have our Birmingham facility, which is our main manufacturing facility. So we have all our CNC machines there. We have our 3D printing facilities there. and everything we need to develop manufacturing software. In Germany, we have our media and entertainment lab. It's actually mainly used for automotive, and Germany is one of the automotive hubs. That's why we build up a studio there to help them work with virtual reality, rendering technologies, and these kind of things. And Australia is the last one. In Australia, we have a facility for material science. Our injection molding team is based in Australia, so they need a lot of material information, and this is why our materials lab is based in Australia. So back to the topic. So when we talk about performance-based designs, the main question is probably, why do we need these new approaches? And some are pretty obvious. I think that now that additive has been around for a while, the designs are getting more complex. People want to achieve even more unique designs, which drives us into computational limitation. So our designs cannot be handled by the software, the computer we're using anymore. There are always new manufacturing processes popping up. So additive was the beginning. Now we're talking about multi-material printing, people starting to talk about 4D printing. So there's still a lot of development in that area. But another thing that's also changing is the environmental impact is getting bigger. So there are real requirements now we need to fulfill to have sustainable products. And I think this aspect has probably grown the most over the last years. But there's also still something like the aesthetics effect, and the design itself is more and more in the front instead of just the pure function of a part. And this all drives a lot of limits, and this is why we need to look into new technologies and new approaches how to design for these problems. So there are many solutions out there. There are many great solutions out there, and we try to tackle it from our own perspective and try to also focus on our own platform we're using. And we can dive into it. So the approach we are taking is called volumetric modeling. On the left side, you see our traditional approach with B-Reps, where you define your boundary representation, you can define sketches, you can extrude them. It's the classic design and how it's built up over decades now. On the right-hand side, you see our volumetric approach, which is basically not represented boundary anymore. So it can be a mathematical description, it can be voxel-based. There are many possibilities how it can be described. But you also see the performance difference. So when you just look at the video and how quickly the software is responding, even when you have really complex structures, this is really the advantage of the new design. It's not just having new structures and being able to design new, it's really also the computational power that comes with it. So when we look at this, we would divide it in 3 categories. The first one is volumetric geometries. So with this approach of modeling, you can create entirely new structures from scratch. You can use simulation data, scan data, a similar approach than generative design, and create completely new parts from scratch without using any sketches or anything. You can describe them by mathematical functions, for example. The second category is optimizing geometry. So, for example, surface patterns or the grids you can see for speakers, as well as textures. These 2 approaches we can also do with traditional CAD. There's no limitation for that. But there is a limitation, as I said, in terms of performance, computational power. And that is why these 2 approaches are super interesting to look at. The third category, is volumetric properties. We call it volumetric properties because everybody has properties. And with these volumetric properties, we can, for the first time, really describe the inside of a body. So we are talking about color, we're talking about material gradients, we're talking about lattice structures. And this is why, for our first approach, we are focusing on that volumetric property field, because this is something that is really difficult to do with traditional CAD and almost impossible. There are specialty tools that can do that today, but you always have to leave your CAD system to do that. So what does it mean, volumetric properties? I think the focus we're taking on that for now is really the additive space, because the biggest advantage is in that area. So describing a multicolor, completely three-dimensional, supporting multi-material printers, that is something that's where the hardware is still ahead of the software and where we need to pick up. Define porosity, so creating lattice structures, as well as supporting 3D textures. So if you want to have a natural texture, like a tree texture, for example, you need a way to tell your machine what to do. And to tell your machine what to do, we are also part of the 3MF consortium. And as you maybe know, it is a new standardized file format for 3D printing. And we onboarded volumetric information. So you now can have a file format where you can also add these informations, like color informations, texture informations, as well as material informations. But how is it for a user? I mean, the biggest question is, how do we open this up for a user to not confuse the user, to not scare the user, to also support the people who are not experts in that field, because that is what you need to be nowadays. And our approach is, we take it simple. You always have described your body with, is it a solid or a mesh body? What kind of color does it have? And which kind of material is it? And we're opening this up now. You can control it. You can tell, I don't want to have one color. I want to have a color gradient. I don't want to have one material. I want to have several materials and want to create a gradient out of it. Or I want to have a porosity because I'm trying to design a bone structure, or just a lattice for light weighting. I need a way to describe it. So this is how we approach it. We're opening up the volume for the user, and they can manipulate it now. The first example, and what went live yesterday, is focused on latticing, because that's the most straightforward one. That's the one everybody's screaming about in additive. So we added that functionality in our platform Fusion. And as you see, it's super simple to use. We broke it down into just a handful of parameters you can change. You have a quick response. You can play with it. You can come up with different solutions. And in the end, you can even take it to your printer and print it, or you can export it and use your slicer. But this was our first approach. How do we simply get people access to create lattice structures, as well as what you can see now, additional skins to it without modeling it and doing it really complicated, just natural CAD environments for beginners. But a lot of people would say this is not enough. I mean, I want to manipulate it. I want to do more. And this is also what is coming. Right now, we offered a tool for our beginners. We offered a tool you can feel comfortable, you can get started with, you can start exploring. But there's more that people want, and there's more to come. So what you see on the right-hand side is our more experimental tool, where we go almost into programming, so where people can type in mathematical descriptions, they can define their own cells. As you saw, we just have some predefined cell shapes right now. So there are more options to define these a lot more. And of course, if you think about it, that is, we go on with color, we want to go on with materials. we don't want to have separate tools for them because they need to interfere. So with a more advanced user interface, you can bring them all together into one part. And you can, for example, here's on the really right side, you see an example where we use simulation results. So you could run a simulation, you could use that as an input, and you can then create your part out of it. You can use it for color mapping. And this is why we think there need to be some more advancement. There need to be something more complex. But we also want to give people the chance to start easy, because it's probably 90% of the time that you're doing the same thing to your parts. And to do that a little bit easier, we gave a standard format people can use. Another thing is thinking about how we can combine it. I mean, now we have all these volumetric possibilities where we can describe the inside of our body. We could combine that with how we create structures outside of our body, so generative design or combining with volumetric, for example. So what can come next, and what are the possibilities we are seeing in the future? We talked about creating new geometries. And I think for creating new geometries, as I already said, we could use simulation results to drive new designs. We could use scan data to create new results. We could enable new technologies that can drive the results. So having a part that's perfectly designed for an HP printer or for an EOS machine. We could also go and start having automated shape generators. So if you want to connect two parts and you don't care how it looks like, you just need a quick connection, you could generate these ones automatically and super quick. The same when we talk about optimizing geometry. So I think there's a lot of potential for example, complex patterns. It's a pain to draw them nowadays and to really come up with unique patterns, for example, logo patterns. It's a lot of work and it takes a lot of time. We could automate some of that and make it a lot more accessible and easy. When you think about a serial number or to detect your parts, having QR codes, so that can all be automated and being much easier with that technology. I'm also thinking about drain holes. So if you want to get rid of your powder, there are some easy ways to do that. We could automate that. And we also talked about textures. I think that's something that will come more and more, and we will see a lot more. So these are just some thoughts and examples of where this technology can go next. On top of that, as you know, or maybe don't, in our CAD platform, we started to onboard all our manufacturing tools because we believe that combining all these tools gives you the real power. That we have a lot of customers that use CNC machining, but they might also want to inspect their parts. They might also have a robot, also have an additive machine, and they at the moment switch to a different software system every time they use it. So to support them, we are putting everything in one platform. We're making it accessible. We're preparing also for things like hybrid manufacturing, when you think about combining additive and subtractive, or having robotics combined with additive. Very common things that are already possible today, but still super complicated in the software. On top of that, we think that the ecosystem is super important. So the design tool is still your base for everything. So having a lot of advanced manufacturing tools is great, but if I cannot design for them, or I need to go into a different version of or a different solution, I might have problems because I have different file formats. I need to export, I need to import, I might lose information because of that. And this is something we want to avoid, and why we are building out this whole platform. And on top of that, I think what is really important to make us successful and prepare us for these really complex structures is we need a data model that is accessible for people. A person executing on a machine needs a different data than the designer, and we need to be able to control that. We need automation so that we are not wasting time to create drawings. This is something that should go automatically, so we can focus on the more important things, how we can save time, save money, how we can optimize our parts perfectly for our machines, and not spending the time for a task nobody wants to do. But we also need intelligent systems. We all know that we can start the same print job twice and it comes out different from that. We need to tell the software how to learn from that. So that's also something that's coming and that needs to come. Another one is independency. I mean, some people are using a Mac nowadays. Other people like to see their information on a tablet. Maybe you're on vacation, but you still want to know what's going on in your project. You want to have access with your phone. So there needs to be a lot more independency. And of course, there are new technologies popping up everywhere. We need to be prepared for them. We need to be able to onboard them as well. And finally, I think we all need to be aware of that not everybody will use our platform and our solution. There are great solutions out there. We need to open up. We need to work better together with our partners. We need to ensure that the data model can be translated into no matter what tool you want to use and give you the independency you need. And I think if this is all in place, and I hope it's in place very soon, then we can really talk about complex structures and how we can prepare for them and how software can really enable new designs. Thank you very much. That was it. As I said, I'm really happy to take questions, and I hope it was interesting. We can definitely dive deeper.
Brilliant. Thank you so much for that, Dominique. We do have some questions, so I'll start from, so I think this one came on quite early on. So they're just asking regarding the file types that you could export some of these files into.
So at the moment, we are focused on mesh file formats because it's the most common one. So 3MF formats you can think of. But the real goal is to have a real connection. So we are also working on a pipeline to our manufacturing tool so you can directly talk to the machine and you don't need to export anymore. That's the end goal for it.
And another question kind of linked to that, I guess, is there a view in the future to feedback machine data into the software tools?
Yes, definitely. So we are also experimenting with machine connectivity, real-time machine connectivity, getting information from the machine. We can then feed into the software and get the information optimized for these informations. That's definitely something that's coming.
Yeah, it's really important. I think there's so much we can learn from past successes and failures that we can definitely use to learn for our future work. Question here is, are you exploring RVE, representative volume elements?
Yes, but that's probably something that will come at a later stage.
And what sort of formats are available for your volumetric models, and how many materials can be handled in a volume-based format?
So the file format that comes in, we don't care. As long as it is a representation, it can come from whatever software. There's no limit. I mean, you could use a generative part and feed it into volumetric. You can use a solid part. You can use a mesh part. It doesn't matter. For the second part of the question, so the material, theoretically, there's no limit how many materials you can feed into it and how your material compose will look like. I think the limit is to understand what we are doing. Simulation software can definitely not handle 5 materials nowadays and a composite of 5 materials or even a gradient of it. So I think this is an area where software still needs to catch up and where we first of all start with mental models to understand what we really need to support this. So I think for now, 2-3 materials in one print job is something realistic, something we can do, something we can handle, something I think somebody who designs it can also still handle. But everything that goes above is probably a limit we still need to explore.
And one more question, this is regarding the software itself. So will it be available for both individual computers offline and in the cloud?
Yes, so as you know, Fusion is our cloud platform. So you have to work in the cloud, but you can set it as offline, you can work offline. So it will be available in both areas. And it will be available in a specific design extension where you have these more expert tools and a normal designer does not necessarily need.
We'll just finish up with this one. So this is regarding electrical circuits. So can you embed electrical circuits into the models and further generate STL files for compatible with slicing softwares?
Good question. I think it should work. I haven't explored yet. We were talking about it, so I think it should work, but I haven't tried. So I'm not giving a definitely yes.
Yeah, no, that's fine. That's great. Thank you so much for your time today, Dominique. It's been really valuable, and thank you so much for being involved.